This is a demonstration of how to run a goodness of fit test on age. First, I'm going to figure out what the bins are. From the LMC 2017 Quick Facts, I have 19 and under is expected to be 36%, 19 and under is expected to be 36%, 20 to 24 is expected to be 34%. 20 to 24 is expected to be 34%. 25 to 49 is 26%, and I'm going to combine that with 50 and over, which is 4%, so 25 and over is going to be 30%. Why did I decide to combine these last two bins? Well, the first time I did not combine them, and it turns out that when I got the expected counts for the chi-squared, the expected counts were not all 5 or greater, so my chi-squared was invalid. So when I do combine these last two bins, I have 30% for 25 and over. Now I need to find the observed counts. So I'm going to go to, I need to find the bins. So the 20 to 24 and 25 and over, this bin from 20 to 25 has a bin width of 5. The easiest way to bin the age data is to make a histogram. So I'm going to make a histogram of the age data with a bin width of 5. And let's start at 5. And let's have StatCrunch put the values of the height of each bar above each bar. And I can see that from age 15 to less than 20, that's 15 to 19, I had 20 people, 20 ages. So from 15 to 19, I had observed 20 people, or 20 ages. From 20 to 24, from 20 to less than 25, that's 20 to 24, I had 15 observations, observed 15 subjects, or 15 people. And 25 and over, so starting at 25, and higher, I had 9 people and 6 people and 6 people and 2 people. 9 plus 6 plus 6 plus 2, that's 15, 21, 23. So I had 23 people. 23. And now I want to make a pie chart of the observed data of the sample. So I'm going to make a pie chart with I've already summarized the data into frequencies, so I'm going to make a pie chart with summary. The categories are in the age list data, and the counts, I want the observed counts, and I'll have the counts and the percents, and I'll compute. And this is my sample data. Actually, it's a fake sample, so I'm going to type fake observed sample data. Okay. And we want to compare that to the expected data. So let's make or the expected, not data, the expected distribution. So let's make a pie chart with a summary of the expected distribution. Let's see, we have the categories in the age, we have the counts in the expected, and they're not actual counts, they're just percentages. So let's just display the percentages. And the title of this will be the expected distribution. And comparing these two pie charts, it looks like the observed sample data and the expected distributions are pretty similar. So that leads me to the hypothesis that the null hypothesis looks like the observed data and the expected distribution might be equal. So now I'm going to run a goodness of fit test, chi-squared test, and I have the observed data in O, I have my expected distribution in E. I'm going to show the expected counts, and here's where I check that all the expected counts are at least 5. If I had separated the 19 and under, the 20 to 24, the 25 to 49, and if I had separated out the 50 and over, the 50 and over expected count would have been less than 5, and my chi-squared goodness of fit would have been invalid. That's why I had to combine the 25 and over, 25 to 49 with a 50 and over, was to make this last number here greater than or equal to 5. My p-value is 0.22, which is greater than my alpha, my significance level of 0.05. So I do not have significant evidence to reject the null hypothesis that the observed distribution is the same as the expected distribution. So we have no reason to believe that the observed distribution is different from the expected distribution. So there's no reason to suspect that there's any age bias in the sampling method. However, we can see from the pie charts that there is a difference between these two, between the observed sample and the expected distribution, but it's not significant. Perhaps if we had had a larger sample size, we would have found a significant difference. But for our sample, a relatively small sample, there is no significant difference between the observed and the expected, and we have no reason to believe that our small sample, we have no reason to believe that there was any age bias in our small sample. And this concludes our chi-squared goodness of fit analysis.